I am the virtual teacher at Egnatia Career College. Today we'll teach branch circuits for the laundry, washroom, and attic, electric heating and air conditioning, oil and gas heating systems. This is video number 12. Branch circuits for the laundry, washroom, and attic. After studying this unit, you should be able to make the proper wiring and grounding connections for large appliances, using various wiring methods. Understand the Canadian Electrical Code (CEC) requirements governing the receptacle outlets for laundry areas. Discuss the CEC rules pertaining to wiring methods in attics. Demonstrate the proper way to connect pilot lights and pilot light switches. Dryer circuit. A separate circuit is provided in the laundry room for the electric clothes dryer. This appliance demands a large amount of power. The special circuit provided for the dryer is indicated on the plans by the symbol on the plans by the symbol of a triangle and letter D. The dryer is connected to circuit B1/B3. Clothes dryer. Clothes dryer manufacturers make many dryer models with different wiring arrangements and connection provisions. All electric dryers have electric heating units and a motor-operated drum, which tumbles the clothes as the heat evaporates the moisture. Dryers also have thermostats to regulate the temperature of the air inside the dryer. Timers regulate the lengths of the various drying cycles. Drying time, determined by the type of fabric, can be set to a maximum of about 85 minutes. Dampness controls are often provided to stop the drying process at a pre-selected stage of dampness so that it is easier to iron the clothes. Clothes dryers create a lot of humid air. Therefore, be sure the dryer is vented to the outside. This residence also has an exhaust fan located in the laundry room. Table 16-1 shows the estimated loads for the various receptacles and fixtures in the laundry, washroom, and attic. The connection of electric clothes dryers is governed by Rule 26-744-2-3. This figure shows the internal components and wiring of a typical electric clothes dryer. A separate receptacle, as shown in CSA configuration 14-30R, Diagram 1, should be installed on the wall adjacent to the dryer. Rule 26-744-3 requires that a cord set as shown in Canadian Standards Association (CSA) configuration 14-30P be used to connect the dryer to the receptacle. A disconnecting means is not required for this appliance, since the attachment plug and receptacle may be used instead of a switch. Rule 26-746-2A. The receptacle can be wired with NMD90 cable if concealed wiring is desired. If the NMD90 is run exposed, it must be protected from mechanical injury. In the residence, the wiring method for the dryer is non-metallic sheathed cable, NMSC, which runs from panel B to a dryer receptacle on the wall behind the dryer. A cord set is attached to the dryer and is plugged into this receptacle. The receptacle and cord have a current carrying capacity that is rated at 125% greater than the dryer rating. A standard dryer receptacle and cord set, as shown in Figure 16-3, is usually rated at 30 amperes, 125/250 volts. This figure shows the correct wiring connections to the terminals on the receptacle. Cords and receptacles rated for a higher current are available. The L-shaped neutral slot of the outlet does not accept a 50 ampere cord set. The receptacle must be flush mounted, if practical, according to Rule 26-744-9. The outlet will fit a 119 by 54 mm square box. Make sure that the box is mounted in the proper orientation to ensure that the appliance cord hangs down and reduces strain on the receptacle. In this residence, the dryer is installed in the laundry room. The schedule of special purpose outlets in the specifications shows that the dryer is rated at 5,700 watts and 122/40 volts. The schematic wiring diagram, Figure 16-2 shows that the heating elements are connected to the 240-volt terminals of the terminal block. The dryer motor and light are connected between the hot wire and the neutral terminal, 120 volts. The motor of the dryer has integral thermal protection. This prevents the motor from reaching dangerous temperatures as a result of an overload or failure to start. Rule 14-610 specifies the overcurrent protection requirements for electric clothes dryers and states that, when fuses are used, they must be time delay D or low melting point fuses P. To determine the feeder rating for the house, the CEC requires that the load included for a dryer be 25% of the nameplate rating, assuming that an electric range has been included. Rule 8-200-1A-7. The branch circuit ampacity is based on the nameplate rating of the dryer. If it is not clear what the load of an appliance is, always base it on the nameplate rating. Conductor size. Rule 26-746-1 states that any appliance rated at more than 1,500 watts shall be supplied from a branch circuit used solely for one appliance. The electric clothes dryer in this residence has a nameplate rating of 5,700 watts. Thus, I is equal to W divided by E. 5,700 divided by 240 equal to 23.75 amperes. If we apply Rule 8-104, that is, to multiply the current rating times 125% to find the required circuit ampacity, and we come to 29.7 amperes. Accordingly, the dryer circuit B1/B3 is a 3-wire, 30 ampere, 240 volt circuit. Consulting CEC Table 2, it can be seen that the conductors in the non-metallic sheath cable that feed the dryer could be number 12 AWG wire if 90 degrees Celsius rated and number 10 AWG wire if 75 degrees Celsius rated. Since all devices in this house are to be hooked up to circuit breakers and since circuit breakers have either a 60 degrees Celsius or 75 degrees Celsius rating, the number 10 non-metallic sheath cable will have to be used. By CEC definition, a branch circuit refers to the circuit conductors between the final overcurrent device and the outlet. Therefore, the conductors between the overcurrent device in panel B and the dryer outlet constitute the dryer's branch circuit. Overcurrent protection. Rule 14-104 states that the branch circuit overcurrent device rating is not to exceed the allowable ampacity of the conductors. The size of the fuse or circuit breaker may be obtained from Table 13. Here, again, the manufacturer of the appliance will mark the circuit overcurrent device rating. If the appliance is not marked, the overcurrent protection shall be in accordance with Rule 4-004 for the conductors. 30 amperes for our example, as discussed above. Bonding frames of ranges in dryers. Rule 10-612-1 requires that the exposed non-current carrying metal parts of portable equipment such as clothes dryers or ranges be bonded to ground. The branch circuit conductors for the dryer are connected to panel B, circuit B1/B3. This is a double-pole circuit that breaks only the two ungrounded conductors. The neutral conductor remains solid and unbroken. Receptacle outlets. Laundry. Rule 26-720 I and 2 requires that at least 2 receptacles be installed in a laundry room, one for a washing machine and at least one more. In the laundry room in this residence, the 15 ampere circuit B11 supplies the receptacle for the washer. Circuit B11 serves no other outlets. The receptacle is not required to be ground fault circuit interrupter (GFCI) protected and is exempt from Rule 26-656, which stipulates that all receptacles 20A or less must be fed from an AFCI protected source. This figure shows the cable layout for the laundry room. Circuit B9 connects to the 2 receptacles in the laundry, which will serve an iron, a sewing machine, and other small portable appliances. Circuit B20 has already been included in the watts per square meter calculations for service entrance and feeder conductor sizing, Rule 8-200-1A, I2. See the complete calculations in Unit 7. Lighting circuit. The general lighting circuit for the laundry and washroom is supplied by circuit B20. The types of vanity lights, ceiling fixtures, and standard wall receptacle outlets, as well as the circuitry and switching arrangements, are similar to those discussed in other units of this text. Exhaust fans. Ceiling exhaust fans are installed in the laundry and washroom and connected to circuit B20. The exhaust fan in the laundry will remove excess moisture resulting from the use of the clothes washer. Exhaust fans may be installed in walls or ceilings. The wall-mounted fan can be adjusted to fit the thickness of the wall. If a ceiling-mounted fan is used, sheet metal duct is recommended between the fan unit and the outside of the house. Any exhaust ducting located in an attic space must be insulated. During the cold season, any moisture that is removed by an exhaust fan will condense in an uninsulated duct. This will lead to premature rusting of the exhaust duct and fan. The moisture can also leak out of the fan or duct, causing serious water damage. The fan unit terminates in a metal hood or grill on the exterior of the house. The fan has a shutter that opens as the fan starts up and closes as the fan stops. The fan may have an integral pull chain switch for starting and stopping, or it may be used with a separate wall switch. In either case, single-speed or multi-speed control is available. The fan in use has a very small power demand, 90 volt amperes. Humidity control. An electrically heated dwelling can experience a problem with excess humidity due to the tightness of the house because of the care taken in the installation of the insulation and vapor barriers. High humidity is uncomfortable. It promotes the growth of mold and the deterioration of fabrics and floor coverings. In addition, the framing members, wall panels, and plaster or drywall of a dwelling may deteriorate because of the humidity. Insulation must be kept dry, or its efficiency decreases. A low humidity level can be maintained by automatically controlling the exhaust fan. One type of automatic control is the humidistat. This device starts the exhaust fan when the relative humidity reaches a high level. The fan exhausts air until the relative humidity drops to a comfortable level. The comfort level is about 50% relative humidity. Adjustable settings are from 0 to 90% relative humidity. The electrician must check the maximum current and voltage ratings of the humidistat before the device is installed. Some humidistats are extra low voltage devices and require a relay. Other humidistats are rated at line voltage and can be used to switch the motor directly. A relay is not required. However, a relay must be installed on the line voltage humidistat if the connected load exceeds the maximum allowable current rating of the humidistat. The switching mechanism of the humidistat is controlled by a nylon element that is very sensitive to changes in humidity. A bimetallic element cannot be used because it reacts to temperature changes only. Wiring. The humidistat and relay for the attic exhaust fan are installed using number 14 NMD90. The cable runs from circuit A10 to a 4 inches square, 1.5 inch deep outlet box located in the attic near the fan. Part B. A motor circuit switch is mounted on this outlet box. This switch unit serves as a disconnecting means within sight of the motor, as required by Rules 28-628-602, 3E. Motor overload protection is provided by the heater unit installed in the motor-rated switch. As an alternative, an AC general-purpose switch rated at 125% of the full load amperes, FLA, of the motor may be used as the disconnecting means. Mounted next to the switch unit is a relay that can carry the full load current of the motor. Extra low voltage thermostat wire runs from this relay to the humidistat. The humidistat is located in the hall between the bedrooms. The thermostat cable is a 2-conductor cable since the humidistat has a single pole, single throw switching action. The line voltage side of the relay provides single pole switching to the motor. Normally, the white grounded conductor is not broken. Although the example in this residence utilizes a relay to use extra low voltage wiring, it is also proper to install line voltage wiring and use line voltage thermostats and humidity controls. These are becoming very popular, with the switches actually being solid-state speed controllers, permitting operation of the fan at an infinite number of speeds between high and low settings. Attic lighting and pilot light switches. It is always good practice to install at least one lighting outlet in an attic and to control it by a switch located near the access point of the attic. The light should have a guard to protect it from injury, or a short flexible drop light may be used. Many attics are used for storage. They may also contain equipment that might need to be serviced, so install a lighting outlet near it. Ambient temperatures in attics can exceed the ratings of some equipment. Any circuit and equipment wiring calculations and requirements must take this into account. Rule 4-0047. Table 16-2, which reproduces CEC Table 5A, shows the derating factors for ambient temperatures greater than 30 degrees Celsius. These must be applied for wiring in attics where the ambient temperature could easily exceed 30 degrees Celsius. The 4 keyless lamp holders in the attic are turned on and off by a single-pole switch on the garage wall close to the attic storable stairway. Associated with this single-pole switch is a pilot light. The pilot light may be located in the handle of the switch or separately mounted. This figure shows how pilot lamps are connected in circuits containing either single-pole or three-way switches. If a neon pilot lamp in the handle, toggle, of a switch does not have a separate grounded conductor connection, it will glow only when the switch is in the OFF position because the neon lamp will then be in series with the lamp load. The voltage across the load lamp is virtually zero, so it does not light, and the voltage across the neon lamp is 120 volts, allowing it to glow. When the switch is turned on, the neon lamp is bypassed, shunted, causing it to turn off and the lamp load to turn on. Use this type of switch when it is desirable to have a switch glow in the dark to make it easy to locate. Installation of cable in attics. The wiring in the attic is to be done in cable and must meet the requirements of Rules 12-500 through 12-526 for non-metallic sheet cable. These rules describe how the cable is to be protected. In accessible attics, see Figure 16-11A. Cables must not be run across the top of floor or ceiling joists as you circled as number 1, run across the face of studs circled as number 2, or rafters circled as number 3 that have a vertical distance between the floor or floor joists exceeding 1 meter. Guard strips are not required if the cable is run along the sides of rafters, studs, or floor joists circled as number 4, provided Rule 12-516(1)(2) is met. Figure 16-11C illustrates a cable installation that most electrical inspectors consider to be safe. Because the cables are installed close to the point where the ceiling joists and the roof rafters meet, they are protected from physical damage. It would be very difficult for a person to crawl into this space or to store cartons in an area with a clearance of less than 1 meter. See Figure 16-11B. Although the plans for this residence do not show a 600 mm wide catwalk in the attic, it is installed. In the future, the owner may decide to install additional flooring in the attic to obtain more storage space. Because of the large number of cables required to complete the circuits, it would interfere with flooring to install guard strips wherever the cables run across the tops of the joists. However, the cables can be run through holes bored in the joists and along the sides of the joists and rafters. In this way, the cables do not interfere with the flooring. Most building codes will not allow manufactured roof systems to be drilled. This includes roof trusses. When running cables through framing members, be careful to maintain at least 32 mm between the cable and the edge of the framing member. This minimizes the possibility of driving nails or screws into the cable. It would be very difficult for a person to crawl into this space or to store cartons in an area with a clearance of less than 1 meter. See Figure 16-11B. Attic exhaust fan circuit. An exhaust fan is mounted in the roof of the house. When running, this fan removes hot, stagnant, or humid air from the attic. It will also draw in fresh air through louvres located in the end gables. Such an attic exhaust fan can be used to lower the indoor temperature of the house by as much as 5 degrees Celsius to 10 degrees Celsius. The exhaust fan in this residence is connected to circuit A10, a 120-volt, 15-ampere circuit in the main panel utilizing number 14 NMD90 cable. The derating factors in Table 5 must be applied because of the high ambient temperature in the attic. Exhaust fans can also be installed in a gable of a house, see Part B in Figure 16-13. On hot days, the air in the attic can reach a temperature of 65 degrees Celsius or more. So it is desirable to provide a means of taking this attic air to the outside. The heat from the attic can radiate through the ceiling into the living areas, raising their temperature and increasing the air conditioning load. Personal discomfort increases as well. These problems are minimized by properly vented attic exhaust fans. Fan operation. The exhaust fan installed in this residence has a 1/4 HP direct drive motor. Direct drive means that the fan blade is attached directly to the shaft of the motor. It is rated 120 volts, 60 Hz, 60 cycles per second, 5.8 amperes, and 696 watts, and operates at a maximum speed of 1050 RPM. The motor is protected against overload by internal thermal protection. The motor is mounted on rubber cushions for quiet operation. When the fan is not running, the louvre remains in the closed position. When the fan is turned on, the louvre opens. When the fan is turned off, the louvre automatically closes to prevent the escape of air. Fan control. Typical residential exhaust fans can be controlled by a choice of switches. Some electricians, architects, and home designers prefer to have fan switches, controls, mounted 1.83 meter above the floor so that they will not be confused with other wall switches. This is a matter of personal preference and should be verified with the owner. The exhaust fan in this residence has this type of control. This figure shows some of the options available for the control of an exhaust fan. A simple on and off switch, A. B. A speed control switch that allows multiple and/or an infinite number of speeds, B. C. A timer switch that allows the user to select how long the exhaust fan is to run, up to 12 hours, C. D. A humidity control switch that senses moisture buildup, D. See the section on humidity control in this unit for further details on this type of switch. E. Exhaust fans mounted into end gables or roofs of residences are available with an adjustable temperature control on the frame of the fan. This thermostat generally has a start range of 21 degrees Celsius to 54 degrees Celsius, and will automatically stop at a temperature 5 degrees Celsius below the start setting, thus providing totally automatic on and off control of the exhaust fan. E. F. A high-temperature automatic heat sensor that will shut off the fan motor when the temperature reaches 93 degrees Celsius, F. This is a safety feature so that the fan will not spread a fire. Connect in series with other control switches. G. A combination of controls. This circuit shows an exhaust fan controlled by an infinite speed switch, a temperature control, and a high-temperature heat sensor, G. The speed control and the temperature control are connected in parallel so that either can start the fan. The high-temperature heat sensor is in series so that it will shut off the power to the fan when it senses 93 degrees Celsius, even if the speed control or temperature control is in the on position. Overload protection for the fan motor. There are several ways to provide running overload protection for the 1/4 horsepower attic fan motor. For example, an overload device can be built into the motor, or a combination overload tripping device and thermal element can be added to the switch assembly. Some manufacturers of motor controls also make switches with overcurrent devices. Such a switch may be installed in any standard flush switch box opening 3 by 2 inch. 76 mm by 51 mm. A pilot light may be used to indicate that the fan is running. Thus, a 2-gang switch box or 4-inch by 1.5 inch. 102 mm by 38 mm square outlet box with a 2-gang raised plaster cover may be used for both the switch and the pilot light. Rule 28-308 states that an automatically started motor having a rating of 1 horsepower or less does not need to have overload protection if the motor on the unit has protection features that will safely protect the motor from damage if it stalls or the rotor locks. This must be indicated on a nameplate located so that it is visible after installation. This would be indicated on this particular fan motor since it does have integral overload protection. Branch circuit short circuit protection for the fan motor. CEC Table D16 specifies short circuit and overload protection for motors. Table 45 lists the full load current in amperes for single-phase AC motors. For a full load current rating of 5.8 amperes. Table D16 shows that the rating of the branch circuit overcurrent device shall not exceed 15 amperes if time delay or non-time delay fuses are used and 15 amperes if standard thermomagnetic circuit breakers are used. The exhaust fan is connected to circuit A10, which is a 15 ampere, 120 volt circuit. This circuit does not feed any other loads. The circuit supplies the exhaust fan only. Time delay fuses sized at 115% to 125% of the full load ampere rating of the motor will provide both running overload protection and branch circuit short circuit protection. If the motor is equipped with inherent, built-in overload protection, the time delay fuse in the circuit provides secondary backup protection, providing double protection against possible motor burnout. Electric heating and air conditioning. After studying this unit, you should be able to list the advantages of electric heating. Describe the components and operation of electric heating systems, baseboard heater, heating cable, furnace. Describe thermostat control systems for electric heating units. Install electric heaters with appropriate temperature control according to Canadian Electrical Code (CEC) rules. Discuss the CEC requirements and electrical connections for air conditioners and heat pumps. Explain how heating and cooling may be connected to the same circuit. General discussion. Many types of electric heat are available for heating homes: unit heaters, boilers, electric furnaces, heat pumps, duct heaters, baseboard heaters, and radiant heating panels. Some of the variables that must be taken into account include construction of the building envelope, type and thickness of the insulation, size of windows, and whether the siding is of brick or wood. Another variable would be in what direction most windows and doors face. One of the most important variables is the location of a house within the country. Each region has a different number of degree days, which affects the heat requirements to maintain a comfortable living temperature. For this residence, the total estimated wattage is 13,000 watts, 13 kilowatts. Types of electric heating systems. Electric heating units are available in baseboard, wall-mounted, and floor-mounted styles. These units may have built-in thermal overload protection. The type of unit to be installed depends on structural conditions and the purpose for which the room is to be used. Another method of providing electric heating is to embed resistance-type cables in the plaster of ceilings or between two layers of drywall on the ceiling, Rules 62-214 through 62-216. Resistance-type heating cables may also be used for melting snow and ice on roof overhangs, eaves troughs, walkways, and driveways, Rule 62-300. Electric heat can also be supplied by an electric furnace and a duct system similar to the type used on conventional hot air central heating systems. The heat is supplied by electric heating elements rather than the burning of fuel. Air conditioning, humidity control, air circulation, electronic air cleaning, and zone control can be provided on an electric furnace system. Many homes are now built or renovated with ceramic tile flooring. Often, heating cable is installed under the tile to eliminate cold floors. It is very important to follow the manufacturer's installation instructions. Although some heat will radiate from the tile into the room, underfloor heating cable sets are not intended to be the sole source of heat for the room. The wattage of the heating cable set is usually quite low, as it is meant to heat only the floor. Separate circuit required. Rule 62-1101A and 26-8061 require that central heating equipment be supplied by a separate branch circuit. This includes electric, gas, and oil central furnaces and heat pumps. The exception to Rules 62-1101 and 26-8061 is equipment directly associated with central heating equipment, such as humidifiers and electrostatic air cleaners, which are permitted to be connected to any branch circuit, Rule 26-806-4. The separate circuit rule is due to the possibility that if the central heating equipment was connected to another circuit, such as a lighting circuit, a fault on that circuit would shut off the power to the heating system. This could cause freezing of water pipes. A disconnecting means must be provided to open all ungrounded conductors to the central heating unit. This disconnect must be within the site of and no farther than 9 meters from the unit, Rule 62-206-5. Control of electric heating systems. Line voltage thermostats can be used to control the heat load for most baseboard electric heating systems. Common wattage limits for line voltage thermostats are 2,500 watts, 3,000 watts, and 5,000 watts. Additional ratings are available. The electrician must check the nameplate ratings of the heating unit and the thermostat to ensure that the total connected load does not exceed the thermostat rating. The wattage limit of a thermostat is found using the amperage formula as illustrated in this slide. When the connected load is larger than the rating of a line voltage thermostat, as in the case of an electric furnace, low voltage thermostats may be used. In this case, a relay must be connected between the thermostat and load. The relay is an integral component of the furnace. The low voltage contacts of the relay are connected to the thermostat. The line voltage contacts of the relay are used to switch the actual heater load. Low voltage thermostat cable is run between the low voltage terminals of the relay and the thermostat. In general, contacts and relays serve the function in the electrical industry of using a low voltage or low current to control a much higher one. This is done for safety and to lower expense, as the smaller control wires of a relay or contactor are much cheaper to run than the large conductors that bring power to heating or cooling devices. When the connected load is larger than the maximum current rating of a thermostat and relay combination, the thermostat can be used to control a heavy-duty relay or contactor. An example of such a relay is the magnetic switch used for motor controls. The load side of the magnetic switch feeds a distribution panel containing as many 15 or 20 ampere circuits as needed for the connected load. A 40 ampere load may be divided into 3 15 ampere circuits and still be controlled by one thermostat. The proper overcurrent protection is obtained by dividing the 40 ampere load into several circuits having lower ratings. Circuit requirements for baseboard units. This figure shows typical baseboard electric heating units. These units are rated at 240 volts, but are also available in 120 volt ratings. The wiring for an individual baseboard heating unit or group of units is shown in this figure. A 2-wire cable, armored cable or non-metallic sheathed cable with ground, would be run from a 240 volt, 2-pole circuit in the main panel to the outlet box or switch box installed at the thermostat location. A second 2-wire cable runs from the thermostat to the junction box on the heater unit. The proper connections are made in this junction box. Most heating unit manufacturers provide knockouts at the rear and on the bottom of the junction box. The supply conductors can be run through these knockouts, using proper connectors for their wiring method. Most baseboard units also have a channel or wiring space running the full length of the unit, usually at the bottom. When 2 or more heating units are joined together, the conductors are run in this wiring channel. Most manufacturers indicate the type of wire required for these units because of conductor temperature limitations. A variety of fittings, such as internal and external elbows, for turning corners, and blank sections, are available from the manufacturer. Most wall and baseboard heating units are available with built-in thermostats. The supply cable for such a unit runs from the main panel to the junction box on the unit. Manufacturers of electric baseboard heaters list blank sections ranging in length from 0.5 meter to 2 meter. These blank sections give the installer the flexibility needed to spread out the heater sections and to install these blanks where wall receptacle outlets are encountered. Location of electric baseboard heaters in relation to receptacle outlets. Approved electric baseboard heaters shall not be installed below wall receptacle outlets unless the instructions furnished with the heaters indicate that they may be installed there, Rule 26-724A, and Appendix B. The reason for this is the possible fire and shock hazard if a cord hangs over and touches the heated electric baseboard unit. The insulation on the cord can melt from the heat. The electrician must pay close attention to the location of receptacle outlets and the electric baseboard heaters in the plans and specifications. Blank spacer sections may be installed, following the CEC requirements for spacing receptacle outlets and just how much, wattage and length, baseboard heating is required. The Canadian Standards Association, CSA, approves the use of factory-installed or factory-furnished receptacle outlet assemblies as part of permanently installed electric baseboard heaters. These receptacle outlets shall not be connected to the heater circuit. Circuit requirements for electric furnaces. In an electric furnace, resistance heating elements are the source of heat. The blower motor assembly, filter section, condensate coil, refrigerant line connection, fan motor speed control, high temperature limit controls, relays, and similar components are similar to those found in gas furnaces. In most installations, the supply conductors must be copper conductors having a minimum 90 degrees Celsius temperature rating, such as type T90. The instructions furnished with the unit will have information relative to supply conductor size and type. Since proper supply voltage is critical to ensure full output of the heating elements, voltage must be maintained at not less than 98% of the unit's rated voltage to provide its rated wattage. Therefore, the voltage drop should not be allowed to exceed 2% of the unit's rated voltage to achieve its rated output. The CEC allows a maximum voltage drop of 3% on a branch circuit, Rule 8-1021A. Many electric furnaces furnish the wattage, or kilowatt, output for more than one voltage level. For every 1% drop in voltage, there will be an almost 2% drop in wattage output. For instance, if a 240-volt rated heater is connected to 208 volts, its actual output of heat is less than its rated watts. The actual voltage at the supply terminals of the electric furnace or baseboard heating unit determines the true wattage output of the heating elements. The effect that different voltages have on electric heating elements is covered in Unit 20. The demand factors for service conductors used to supply heating equipment are set out in Rule 62-118, which requires service conductors to have an ampacity not less than the current ratings of all of the equipment supplied. In the case of an electric furnace, this would be 100% of the total connected load, Rule 62-118-4. If baseboard heating is being used, Rule 62-18-3 allows the ampacity of the main service conductors to be reduced. If each room or heated area is thermostatically controlled, the demand factor is 75% for each kW above 10 kilowatts. So, if the total connected load was 20 kilowatts for baseboard heating with thermostats in each room, the demand load must be calculated as illustrated in this slide. Total demand load equal to 17.5 kilowatts. These demand watts would be applied to the service conductors. Two or more heating fixtures, such as baseboard heaters, may be connected on a single heating branch circuit, provided that the overcurrent device does not exceed 30 amperes. Therefore, the maximum load on each branch circuit is 80% or 24 amperes or 5,760 watts at 240 volts, Rule 62-114-6. The electric furnace must be supplied by an individual branch circuit, Rule 62-110. The separate circuit requirement pertains to any type of central heating, including oil, gas, electric, and heat pump systems, Rule 26-806. Heat pumps. A heat pump cools and dehumidifies on hot days and heats on cool days. To provide heat, the pump picks up heat from the outside air, which it adds to the heat created by the compression of the refrigerant. This heat is used to warm the air flowing through the unit, which is then delivered to the inside of the building. The heat pump can also be used to cool the building when the outside air temperature is warm. To achieve this, the direction of flow of the refrigerant is reversed. Warm air is then delivered to the outside, and the house is cooled. Heat pumps are available as self-contained packages that provide both cooling and heating. In the Canadian climate, the heat pump alone may not provide enough heat. Therefore, the heat pump may use supplementary heating elements contained in the air handling unit, or be used in combination with a forced air gas furnace. Bonding. Bonding of electrical baseboard heating units and other electrical equipment and appliances has been covered previously in this textbook. Refer to Rule 10-600. Marking the conductors of cables. Two-wire cable contains one white conductor, one black conductor, and one bonding conductor. Using two-wire cable to supply 240-volt electric baseboard heaters appears to violate the CEC. However, according to Rule 4-0301, two-wire cable may be used for the 240-volt heaters if the white conductor is permanently marked as ungrounded by paint, colored tape, or other effective means. This is necessary, since people may assume that an unmarked white conductor is a grounded circuit conductor having no voltage to ground. However, the white wire in the heater circuit is connected to a hot phase and has 120 volts to ground. Therefore, a person can be subject to a harmful shock by touching this wire and the grounded baseboard heater, or any other grounded object, at the same time. Most electrical inspectors accept black or red paint or tape as a means of changing the color of the white conductor. The white conductor must be made permanently unidentifiable at every accessible point, such as at heater and service panels. A more commonly used method is to install two-wire cable with black and red conductors. One such cable is heated, a red-sheathed NMSC cable manufactured by Nexans Incorporated, specifically designed for heating circuits. Unit 6 also addresses wire color coding. Room air conditioners. For homes without central air conditioning, window or through-the-wall air conditioners may be installed. These room air conditioners are available in both 120-volt and 240-volt ratings. Because room air conditioners are plug-and cord connected, the receptacle outlet and the circuit capacity must be selected and installed according to the CEC. The basic CEC rules for installing these units and their receptacle outlets are: the air conditioners must be grounded. The air conditioners must be connected using a cord and attachment plug. The rating of the branch circuit over current device must not exceed the branch circuit conductor rating or the receptacle rating, whichever is less. The air conditioner load shall not exceed 80% of the branch circuit ampacity if no other loads are served. The attachment plug cap may serve as the disconnecting means, Rule 28-602-3C. Receptacles for air conditioners. This figure shows three types of receptacles that can be used for air conditioning installations. A. Shows a 20 ampere, 250-volt receptacle for use on a 240-volt installation. B. A 20 ampere, 125-volt receptacle for use with a 120-volt air conditioner circuit. And C. A 15 ampere, 250-volt receptacle for use with a 240-volt installation. Diagram 1 illustrates the many different voltage/ampere receptacle configurations. Central heating and air conditioning. The residence used as an example in this textbook has central electric heating and air conditioning, consisting of an electric furnace and a central air conditioning unit. The wiring for central heating and cooling systems is shown in this figure. One branch circuit runs to the electric furnace, and another runs to the air conditioner or heat pump outside the dwelling. Extra low voltage wiring is used between the inside and outside units to provide control of the systems. The extra low voltage class 2 circuit wiring must not be run in the same raceway as the power conductors, Rule 16-212-1. Special terminology. These terms pertain to air conditioners, heat pumps, and other hermetically sealed motor compressors. Rated load current is the current drawn when the unit is operating at rated load, at rated voltage, and at rated frequency. Branch circuit conductor ampacity is based on the rated load current, which must be marked on the label, Rule 2-100-1D. This will determine size, and short circuit and ground fault protective device ratings. Rule 2-100-5 requires that approved equipment be used only in accordance with instructions included in the original approval of the equipment. For example, the nameplate of an air conditioning unit reads maximum size fuse 40 amperes, so only 40 ampere fuses can be used. 40 ampere circuit breakers are not permitted. If the nameplate called for maximum overcurrent protection, either fuses or circuit breakers could be used. The air conditioner requires a motor-rated disconnect to be installed within 3 meters and within sight of the unit, Rule 28-604-5. Loads not used simultaneously. Heating and air conditioning loads are not likely to operate at the same time. Therefore, when calculating feeder sizes to an electric furnace and an air conditioner, you need to consider only the larger load. In Rule 8-106-3, the words "where it is known" refer to the fact that common sense would dictate that heating and air conditioning would not be in use at the same time. The larger connected load is used to calculate the demand on the service feeders. If the air conditioning has the larger demand, this demand is used at 100%. If the heating demand is greater, this is used to calculate the demand watts according to Rule 8-106-4 and Rule 62-118. Oil and gas heating systems. After studying this unit, you should be able to understand the basics of gas and oil heating systems. Identify some of the more important components of gas and oil heating systems. Interpret basic schematic wiring diagrams. Explain the principles of the thermocouple and the thermopile in a self-generating system. Understand and apply the requirements for control circuit wiring, CEC Section 162. Heating a home with gas or oil is possible with warm air, fan-forced warm air or gravity. Hot air rises naturally. Hot water, hydronic, hot water circulated through the piping system by a circulating pump. The system uses tubing embedded in the floor or radiators that look very much like electric baseboard heating units. Principles of operation. Most residential gas or oil heating systems operate as follows. A room thermostat is connected to the proper electrical terminals on the furnace or boiler, where the controls and valves are interconnected to provide safe and adequate heat to the home. Some typical wiring diagrams are shown in these figures. Most residential gas or oil heating systems are packaged units in which the safety controls, valves, fan controls, limit switches, and so on are integral, pre-assembled pre-wired parts of the furnace or boiler. For the electrician, the field wiring generally consists of installing and connecting the wire to the thermostat, and installing and connecting the power supply to the furnace or boiler. Major components. Gas-fired and oil-fired warm air systems and hot water boilers contain many components. Aquastat. This direct immersion water temperature thermostat regulates boiler or tank temperature in hydronic heating systems, ensuring that the circulating water maintains a satisfactory temperature. CAD cell. A photoconductive flame detector. Detector must be installed so that it can see flame. Connects to primary control system. Circulating pump. Circulates hot water in a hydronic central heating system. Combustion chamber. Surrounds the flame and radiates heat back into the flame to aid in combustion. Combustion head. Creates a specific pattern of air at the end of the air tube. The air is directed to force oxygen into the oil spray so the oil can burn. A combustion head, also referred to as the turbulator, fire ring, retention ring, or end cone. Control circuit. Any electric circuit that controls any other circuit through a relay or an equivalent device, also referred to as a remote control circuit. Draft regulator. A counterweight swinging door that opens and closes to help maintain a constant level of draft over the fire. Fan control. Controls the blower fan on forced warm air systems. On newer furnaces, the fan control is an electronic timer that starts the fan motor a given time in seconds after the main burner has come on. This timing ensures that the blower will blow warm air. Older adjustable temperature fan controls still exist. Fan motor. An electric motor that forces warm air through the heating ducts. In typical residential heating systems, the motor is provided with integral overload protection. The motor may be single, multiple, or variable speed. Flow valve. Prevents gravity circulation of water through the piping system. Flue. A channel in a chimney or a pipe for conveying flame and smoke to the outer air. Heat exchanger. Transfers the heat energy from the combustion gases to the air in the furnace or to the water in a boiler. High temperature limit control. A safety device that limits the temperature in the plenum of the furnace to a safe value predetermined by the manufacturer. When this temperature is reached, the control shuts off the power to the burner. In newer furnaces, the control is part of an integrated circuit board and is communicated to by a sensor strategically located in the plenum. Some older furnaces have individual high-temperature limit controls and a separate fan control, others have combination high-temperature limit/fan controls. Hot surface igniter. Heats to a cherry red/orange color in furnaces without a standing constant pilot light. When it reaches the proper temperature, the main gas valve is allowed to open. If the hot surface igniter does not come on, the main gas valve will not open. Most energy-efficient furnaces use this kind of ignition. Hydronic system. A system of heating or cooling that involves transfer of heat by circulating fluid such as water in a closed system of pipes. Ignition. Continuous pilot ignition. The igniter is designed to stay on continuously. Intermittent duty ignition. Defined by UL 296 as ignition by an energy source that is continuously maintained throughout the time the burner is firing. The igniter is on the entire time the burner is firing. Interrupted duty ignition. Defined by UL 296 as an ignition system that is energized each time the main burner is to be fired and energized at the end of a time trial for ignition period or after the main flame is proven to be established, the igniter comes on to light the flame. After the flame is established, the igniter is turned off and the main flame keeps burning. Induced draft blower. When the thermostat calls for heat, this blower first expels any gases remaining in the combustion chamber from a previous burning cycle. It continues to run, pulling hot combustion gases through the heat exchangers, and then vents the gases to the outdoors. Integrated control. A printed circuit board that contains many electronic components. When the thermostat calls for heat, the integrated circuit board takes over to manage the sequence of events that allow the burner to operate safely. Low water control. Also called a low water cutoff, this device senses low water levels in a boiler. When a low water situation occurs, this control shuts off the electrical power to the burner. Main gas valve. Allows the gas to flow to the main burner of a gas-fired furnace. It may also function as a pressure regulator, a safety shutoff, and the pilot and main gas valve. Should there be a flameout, if the pilot light fails to operate, or in the event of a power failure, this valve will shut off the flow of gas to the main burner. Nozzle produces the desired spray pattern for the particular appliance in which the burner is used. Oil burner breaks fuel oil into small droplets, mixes the droplets with air, and ignites the resulting spray to form a flame. Primary control controls the oil burner motor, ignition, and oil valve in response to commands from a thermostat. See Figure 18-3b. It monitors safety devices such as the flame detector and also monitors the status of the high temperature limit. If the oil fails to ignite, the controller shuts down the oil burner. Pump and zone controls regulate the flow of water or steam in boiler systems to specific zones in the building. Safety controls such as pressure relief valves, high temperature limit controls, low water cutoffs, and burner primary controls protect against appliance malfunction. Solenoid, an electrically operated device. When the valve coil is energized, a magnetic field is developed, causing a spring-loaded steel valve piston to overcome the resistance of the spring and immediately pull the piston into the stem. The valve is now in the open position. When de-energized, the solenoid coil magnetic field instantly dissipates, and the spring-loaded valve piston snaps closed, stopping oil flow or gas flow to the nozzle. The flame is extinguished, allowing fuel to flow. Usually a spring returns the valve back to the closed position. Spark ignition. The spark comes on while pilot gas flows to the pilot orifice. Once the pilot flame is proven through an electronic sensing circuit, the main gas valve opens. Once ignition takes place, the sensor will monitor and prove existence of a main flame. If the main flame goes off, the furnace shuts down. Energy-efficient furnaces may use this for ignition. Switching relay used between the low-voltage wiring and line-voltage wiring. When a low-voltage thermostat calls for heat, the relay pulls in, closing the line-voltage contacts on the relay, which turns on the main power to the furnace or boiler. Usually they have a built-in transformer that provides the low-voltage class 2 control circuit. Thermocouple. In systems that have a standing pilot, a thermocouple holds open a gas valve pilot's solenoid magnet. A thermocouple consists of two dissimilar metals connected together to form a circuit. The metals might be iron and copper, copper and iron constantan, copper-nickel alloy and chrome-iron alloy, platinum and platinum-rhodium alloy, or chromyl and aluminum. The types of metals used depend on the temperatures involved. When one of the junctions is heated, an electrical current flows. To operate, there must be a temperature difference between the metal junctions. In a gas burner, the source of heat for the thermocouple is the pilot light. The cold junction of the thermocouple remains open and is connected to the pilot's safety shut-off gas valve circuit. A single thermocouple develops a voltage of about 25 to 30 direct current (DC) millivolts. Because of this extremely low voltage, circuit resistance is kept to a very low value. Thermopile. More than one thermocouple connected in series is a thermopile. The power output of a thermopile is greater than that of a single thermocouple, typically either 250 or 750 DC millivolts. For example, 10 thermocouples, 25 DC millivolts each, connected in series result in a 250 DC millivolt thermopile. 26 thermocouples connected in series results in a 750 DC millivolt thermopile. Thermostat. A thermostat turns the heating/cooling system on and off. Programmable thermostats might have day or night setback settings, temperature, humidity, and time displayed. Thermostats are usually mounted about 1.3 meters above the finished floor. Do not mount thermostats in areas influenced by drafts or air currents from hot or cold air registers, near fireplaces, near concealed hot or cold water pipes or ducts, in the direct rays of the sun, or on outside walls. Some thermostats contain a small vial of mercury that tips. So the mercury closes the circuit by bridging the gap between the electrical contacts inside the vial. These thermostats must be kept perfectly level to ensure accuracy. Warning: do not throw mercury thermostats into the trash. Mercury is a hazardous waste material and must be given to a waste management organization for proper disposal. Transformer transforms the branch circuit voltage to extra low voltage. For residential applications, these are Class 2 transformers, 120 volts to 24 volts. The low voltage wiring on the secondary of this transformer is Class 2 wiring. Water circulating pump. In hydronic, wet systems, a circulating pump circulates hot water through the piping system. Multi-zone systems have more than one pump, each controlled by a thermostat for a particular zone. In multi-zone systems, a high-temperature control aquastat might be set to maintain the boiler water temperature to a specific temperature. Some multi-zone systems have one circulating pump and use electrically operated valves that open and close on command from the thermostats located in a particular zones. Self-generating millivolt system. Several manufacturers of gas burners provide self-generating systems on decorative appliances such as gas fireplaces. These systems do not require an outside power supply. This figure shows the wiring diagram of a typical self-generating system. The components are connected in series. The small amount of energy required by the gas valve is supplied by a thermopile. Many of these burners are pre-wired at the factory, so the only wiring at the site is done by the electrician, who runs an extra low voltage cable to the thermostat. This system is not affected by a power failure because there is no outside power source. Self-generating systems operate in the millivolt range, typically 250 or 750 MV. A special thermostat is required to function at this extra low voltage level. All other components of the system are matched to operate at the low voltage. Supply circuit wiring. The wiring for the branch circuit for heating equipment that uses solid, liquid, or gaseous fuel is covered in CEC Rules 26-800 through 26-808. The branch circuit wiring must be adequate for the power requirements of the motors, fans, relays, pumps, ignition, transformers, and other power-consuming components of the furnace or boiler. The sizing of conductors, overcurrent protection, conduit fill, and so on has been covered in other units of this textbook. The basic requirements for the branch circuit are: the power for the heating unit and associated equipment must be supplied from a single circuit. For exceptions, see Rule 26-806, 1, 2. A suitable disconnecting means is required. The branch circuit breaker in the panel may be used as the disconnecting means if no one has to walk past the furnace to reach the breaker. If a separate disconnecting means is required, it cannot be mounted on the furnace or in a location that would require a person to walk past the furnace to operate it. The switch must be marked to indicate that it controls the furnace would require a person to walk past the furnace to operate it. Control circuit wiring. CEC Section 16 covers 4 types of control circuits. Class 1 and 2 remote control circuits. Class 1 and 2 signal circuits. Class 1 extra low voltage power circuits. Class 2 low energy power circuits. Rule 26-804 and Appendix B give excerpts from CSA Standard C22.2 No. 3 entitled Electrical Features of Fuel Burning Equipment. Rule 4.8.8 of this standard states that a safety control shall interrupt the current in the ungrounded conductor of the circuit between the overcurrent protection and the load. This must be provided for in the control circuit connected to the Class 2 transformer. As soon as the conductors for remote control, signaling, or power-limited circuits leave the equipment, they are classified as Class 1 or Class 2 circuits. Rule 16-002. There are different requirements for Class 1 and Class 2 circuits regarding wire sizes, derating factors, overcurrent protection, insulation, wiring methods, and materials that differentiate control circuit wiring from regular, normal, light and power circuits, sections 4 and 12. In Part A in this figure, the control circuitry is contained completely within the equipment, so none of the control wiring is governed by Section 16. In Part B in this figure, the control wires leave the equipment. These conductors are classified as Class 1 or Class 2, depending on voltage, current, and other issues discussed in Section 16. Motor control circuits may be protected by control fuses in the controller. When number 16 and number 18 conductors of a Class 1 circuit are run between pieces of equipment, they must be protected by overcurrent devices rated or set at not more than 10 and 5 amperes, respectively. This figure shows a Class 1 circuit where the failure of equipment or wiring, such as high limit and low water controls, would introduce a direct fire or life hazard. Rule 16-010, the circuit is deemed to be a Class 1 circuit. Because of this potential hazard, Rule 16-116 requires that the wiring be installed in rigid or flexible metal conduit (EMT) or armored cable, or be otherwise suitably protected from physical damage. See Rule 16-100 through 16-118 for requirements applicable to Class 1 circuits. Class 1 remote control and signaling circuits may be supplied from a source having a maximum voltage of 600 volts. Class 1 extra low voltage power circuits are limited to 30 volts and 1000 volt amperes, Rule 16-100. The conductors of Class 1 circuits and power conductors may be run in the same raceway only if they are connected to the same equipment. And the Class 1 conductors have the same voltage rating as the highest rated wire in the raceway. Rule 16-114. Most wiring diagrams for residential air conditioning units indicate that their extra low voltage circuitry is Class 2, in which case the field wiring of the power and extra low voltage circuits must be run separately. This figure shows a Class 2 circuit, where the wiring runs to the thermostat. This will be done with LVT wire as listed in CEC Table 19. Type ELC cable is not approved for heating control circuits. Rule 16-210, but would be suitable for door chimes. Table 57 lists the allowable ampacities for Class 2 copper conductors. Note that the derating factors for more than 3 wires or an ambient temperature above 30 degrees Celsius are the same as in Table 5A and Table 5C. For example, a #16/4 LVT cable at 35 degrees Celsius has the following ampacity. Temperature derating from Table 5A, Column 2. 10 amperes times 0.82 equal 8.2 amperes per conductor. Table 57 correction factor for 4 to 6 conductors. 8.2 amperes times 0.8 equals 6.56 amperes per conductor. Class 1, Class 2, and communication cables include CIC, ACIC, control, and instrumentation cable. LVT and ELC Class 2 remote control, signaling, and power limited cables, type FAS 90 power limited fire protective signaling cables. Type MP multipurpose cables. Other communication cables are listed in CEC Table 19. Conductors for Class 2 circuits are not permitted to be run in the same raceway, enclosure, box compartment, or fitting with the regular lighting circuits, power circuits, or Class 1 circuit wiring, Rule 16-212-13. Sometimes it is tempting to cut corners by installing Class 2 conductors in the same raceway as the power conductors. Even if the Class 2 conductors were insulated with 600-volt insulation, the same as the power conductors, this is a violation of Rule 16-212-3. It is permitted to fasten a Class 2 extra low voltage control cable to a conduit containing the power conductors that supply a furnace or similar equipment. Type ELC conductors in Class 2 wiring are not permitted for heating control circuits, Rule 16-210-3. Conductor sizing and overcurrent protection requirements are found in subsection 16-100 for Class 1 circuits. and subsection 16-200 for Class 2 circuits. Transformers that are intended to supply Class 2 circuits are listed by UL and approved by the Canadian Standards Association (CSA) and are marked Class 2 transformer. This figure illustrates the definitions of remote control, signaling, and power limited terminology.